We are moving into section 1.5 on transformations of functions. We saw in section 1.1 where we were looking at basic functions, sometimes what we call those as parent graphs. And we looked at all different kinds, and we're going to review those just again, because what we're going to do in this section is we're going to transform those functions. So we're going to be moving them left to right, we're going to be moving them up and down, we're going to be flipping them possibly, and then also being able to kind of size them in a different way. So let's first talk about those common functions that we saw in section 1.1. The first one being a constant function. So if you recall, if we do like f of x equaling c, call this c instead of 2. Remember that constant function was a horizontal line moving left to right at that c value. So in this case, this specific one, when I had it at 2, would be f of x equals 2. Now, if I look at the identity function, that is if I have f of x equals x, or that f of x equals the y value. Now, what that means is in the t-table, if you wanted to, you could look at like 0, 1, and 2. When you put 0 in there, you kick out 0. When you put 1 in there, you kick out 1. When you put 2 in there, you kick out 2. And so what you see with those points, if you were to plot those at 0, 0, 1, 1, 2, 1, that you have a nice straight line, hence a linear function, in which it bisects basically the first and the third quadrants. For our absolute value function, we had f of x is equal to the absolute value of x. And so, again, you can look at a t-chart of that, and remembering that the absolute value is the distance from 0. So we have, putting in 0, the absolute value of 0 is 0. Putting in 1, the absolute value is 1. Putting in 2, the absolute value of 2 is 2. So it kind of looks like the linear function that we just did. But remember that the absolute value, if you go into the negatives, negative 1, negative 2, if you throw negative 1 in there, the absolute value of that is 1. You throw negative 2 in there, the absolute value is 2, because distance is always positive. So plotting those other 2 points, we get that V shape that we saw out of section 1.1. Now remember, this is a symmetric function. So basically, if you have this point here, you can match it over the y-axis with its corresponding point. Then I have this point. I also have that point. So you kind of get a 2-for-1 deal, which is helpful because really you only have to graph half of those points, and then you can match the other ones to get the rest. So we also have, oops, I was going to do a y equals, but let's do f of x equals x squared for our parabola function. And that is our U shape that we have. Instead of a V shape, we have a U shape. So I kind of like to look at also some of those values. If I throw 0 in, I square that, I get 0. If I throw 1 in, 1 squared is 1. If I throw 2 in, 2 squared is 4. And with this U shape, we are also, just like the absolute value, symmetric over that y-axis. So if I plot 0, 0, 1, 1, 2, 4, I get this half of my parabola. But because it is symmetric, again, we kind of get a 2-for-1 deal, and I can match those other points over there. So that's very helpful when you're working with transformations, and it's all about patterns, and it's all about being able to kind of simplify our graphing to where we don't have to plug in those values all the time when our functions become pretty complex. All right, next one, f of x equals the square root of x. So if you recall, these are going to be kind of opposites of each other, and it will look very similar to this chart, except some things will change. If I throw 0 in there, square root of 0 is 0. If I throw 1 in there, the square root of 1 is 1. If I throw 4 in there, I'm changing it up, the square root of 4 is 2, because that's what's going to kick out a whole number for me. So these 2 charts with the quadratic and with the square root are very similar, except for the only one you can really see it is the last point kind of gets flipped. So we have 0, 0, 1, 1, and 4, 2 gives me that square root function. So here, this is only kind of half of a parabola. If I were to kind of do this, that would make a full one. But for the square root, we only get this piece here, okay? If I did the other part, it would not be a function. All right, f of x is equal to x to the third power for our cube function. And for that table, it is kind of different when we talk about even and oddness at the end of this section. You'll kind of see over the origin symmetry what we have. So a chart that we can remember for this one, and you really only, again, kind of have to remember these pieces as long as you remember kind of it's symmetric over the origin. -2 cubed, so multiply -2 by itself 3 times gives us -8. -1 times -1 times -1 is -1. 0 cubed is 0. 1 times 1 times 1 is 1. And 2 times 2 times 2 is a positive 8. So notice with these 2 points here that the opposites of both coordinates also are created as points. So we have 0, 0 for our cubic. This is what we end up having called an inflection point. Over 1, up 1 gives me another point. Over 1 and down 1 gives me another point. Over 2 and up 8, which let's say is about there. And over 2 and down 8, which gives me something like that. So my cubic was that squiggle function that we had. And so key point there is remembering your turnaround point. Over 1, up 1, over 2, up 8, and then do the opposite of that to get our little squiggle going on there. Okay? All right, the next piece here we have is our cube root function, which looks very similar to our x cubed function, except for just like these points were turned around, these points are going to be turned around for our x cubed. So I'm going to do that kind of over here if I can squeeze that in. That gives me a -8, -1, 0, 1, and 8. That would give me a -2, -1, 0, 1, and 2. So if I plot each one of those points, I'm going to do it in a different color because I think I'm going to go over my t-chart here. We have the exact same points that we started with. Instead of it going this direction, now I have to go -8, -2. So let's say that that's about there. And 8, 2, let's say, is about there. So what I get is kind of a sideways squiggle there, okay, for that cube root of x. So you should have seen all of those in section 1.1. We were identifying those, looking at what the tables look like so that we could kind of get familiar with them. Now, as we review those, we are now going to start looking at transformations of those. So the first transformation that we're going to investigate is a vertical shift. Okay, now I have f of x equals x squared plus 1. So it looks very similar to my f of x equals x squared. But now I'm adding 1 to all of those y values that I got when I squared each of those x values. So I'm going to kind of do a t-chart here just so we could kind of see what happens. I'm going to go -2, -1, 0, 1, and 2. And let's plug those in quickly into our function to figure out what our output y values are. And again, you can do this all day long. You can make a t-chart, plug in values, but I'm telling you, it takes so much longer in order to do that and to be able to kind of find exactly where your graph is. If you know the patterns and kind of these generalizations of what happens on these functions, it becomes a lot easier. So if we throw -2 in and square it, we get a 4 plus 1 is 5. If I put -1 times -1 in there, that's a 1 plus 1 is a 2. 0 squared is 0 plus 1 is 1. 1 squared is 1 plus 1 is 2. And 2 squared is 4 plus 1 is 5. So if I'm going through and I'm going to graph these points, -1, 2, 0, 1, 1, 2, and 2, 5, I get this graph right here. Now, how does that compare to the original? Now, the original was at 0, 0, 1, 1, 2, 4, so I end up having something that looks like this. Well, from the original red graph, what happened to the blue graph? The blue graph moved up by 1, and it moved up by 1 in all the points that I have there. So this plus 1 at the end tells me that the original graph, x squared, went up by 1. Now, let's see. Over here with g of x says I have x squared minus 3. So similarly, what do we think that this minus 3 is going to do to that function? Well, let's see. Let's do a t-chart real quick and see what happens to our values and see if that original x squared goes in a certain way by 3. So if I square negative 2, I get 4 minus 3 is 1. Negative 1 squared is 1 minus 3 is negative 2. 0 squared is 0 minus 3 is negative 3. 1 squared is 1 minus 3 is negative 2. And 2 squared is 4 minus 3 is positive 1. So let's graph all these. Negative 2, 1. Negative 1, negative 2. 0, negative 3. 1, negative 2. And 2, 1. So here is my U shape. Now, what happened there on that U shape if I were to graph those points? Sorry. If I were to graph those points like I should, notice here, or actually go through my points like I should, notice what did our original U shape? Our original U shape was kind of here. Now what happened to, say, this vertex? We went down 1, 2, 3 to this new point here. So this minus 3 constitutes a vertical shift by 3. Now notice with the plus here, I went up 1. With the minus 3, I went down 3. So it's kind of keeping us in check with those same signs that if it is a plus, we're going up. If it is a minus, we are going down. So in general, in order to do a vertical transformation, we're going to let f be a function and c be any positive real number. Then y equals our original function. In this case, we had an x squared, but I could do anything. I could do the square root. I could do the cube root. I could do a linear one. But if I take my function and I add c to it, then that takes the original up by c. So we're moving up, vertically shifting up. If I have y equals f of x minus c, then that takes my original graph down. That's supposed to be down by c. Okay, so plus a number goes up, minus a number goes down. So let's kind of keep that in our toolbox. Let's add a transformation and we're going to kind of put things together, okay? This time we're going to look at a horizontal shift. And notice for these next two functions, notice where the numbers are. The numbers are inside my set of parentheses and I have that square on the outside. So that means I'm still going to be working with my parabola, but what's going to happen to that parabola if I have a minus 2 in with the x and a plus 1 in for the x as well? So let's investigate with a t-chart. And I'm going to kind of look at some of those common points that I already looked at, and let's see if we can get a graph on there. So if I do negative 2 and I subtract 2, so negative 2 and subtract 2, I get negative 4. Negative 4 squared gives me a 16. If I put negative 1 in there, minus 2, that gives me negative 3 squared is a 9. 0 minus 2 is negative 2, squared is a 4. If I put 1 in there, minus 2, I get negative 1, squared is a positive 1. And then when I put 2 in there, 2 minus 2 is 0, 0 squared is 0. So if I were to graph these points, obviously these two are kind of off the chart. If I go 0, 4, 1, 1, 2, 0, notice I don't have a U shape there, but it has a square at the top, so I know that that square has to be a U shape with a parabola. What happens if I keep going further? What if I throw 3 in there? Let's see if we can get a turnaround point. If I throw 3 in there, minus 2, I get 1. 1 squared is 1. So if I have 3, 1, there's that point. Oh, that's looking really good because I see kind of a U shape going here. Let's kind of see what happens when I put 4 in there. 4 minus 2 is 2. 2 squared is also a 4. So I end up getting this piece right here. And notice there is my U shape. That's really good. Now, what do we know has happened from the original parabola, which looks something like this, okay? That original parabola from my turnaround point here has now moved over 1, 2, constituting a horizontal shift. But look what is inside. If we move to the right, That's usually by adding something, but notice in my function, I have a -2. That's going to be important to kind of remind ourselves. So we look at seeing a horizontal shift in the f function. Now, looking at the g function, kind of doing the same thing. Let's look at some of these values that we've looked at so before, just to investigate and see what happens. If I put -2 in here and add 1, that gives me -1 squared gives me 1. If I throw -1 in there plus 1, I get 0, 0 squared is 0. If I put 0 in there, 0 plus 1 is 1, 1 squared is 1, 1 plus 1 is 2, 2 squared is 4, and 2 plus 1 is 3, 3 squared is 9. Again, to eliminate this t-chart, that's why we're investigating these patterns. Now, if I were to graph each of these points, -2, 1, -1, 0, 0, 1, 1, 4, and 2, 9 is off the chart. But notice I do kind of have that U shape forming there. What happens if I throw in -3? So let's see if I can get this common 4. -3 plus 1 is -2. -2 times -2 does give me a +4. Therefore, that also solidifies the idea that I do have that U shape forming in this graph. Now, what happened from the original? The original here, again, kind of comes in this direction. What did I do from here to here? Well, I moved left by 1. But in my equation, it says a +1. So here's what you're going to have to be doing. When you see things inside with your variable, in order to do the correct shift, you have to do the opposite of what your eyes are looking at. So this says a -2. Inside that says I'm going to have a shift to the right by 2. If this is a +1, we have a shift to the left by 1. Now, what happened on that vertical on the back page, or on the last page, remember, those signs symbolize the correct direction that you had to go. You had to go up 1 with the plus and down 3 with the minus. But you have to remember, if you're grouped with the X, these are the ones that are going to be a little bit different. Take the opposite of what you're looking at. So, for our horizontal transformation, we're going to let f be a function and c be a real number. Then our graph, y equals f of x minus c. So inside there, with the x value, grouped with the x value, it takes our original, take the opposite of what we're looking at. It's going to go to the right by c. And we have a graph, y equals f of x plus c. That's going to take our graph to the left by c. So anytime it's grouped with that x, sorry that keeps doing that. Anytime it's grouped with that x inside with the letter, you are going to have a horizontal shift. So let's talk about this next graph. This next graph is an absolute value. Go back to your basic graphs, and that is one of our V-shaped graphs. And it says absolute value of x minus 4. That -4 is outside of those absolute values. It is at the end. So this is one of those graphs where it's going to be a vertical shift because it is at the outside piece added or subtracted with our function. So the original absolute value, looks something like this. Similar to that. We're going to go more like that. Hang on. I'm just going to redo that. All right. Absolute value kind of bisects that first quadrant and bisects the second quadrant. All right, that's the original absolute value. This function tells me I'm going to go down by 4. Knowing that that is my vertical shift, I'm going to go 1, 2, 3, 4. Then I'm going to have over 1, up 1, over 1, up 2 was our pattern that we had on our basic graph. And then we knew it was symmetric, so we get a 2 for 1 deal, and we can graph just an estimate. We're not doing all the points. Get enough points where you can know how to where it's going to go and be done with it. Okay? So this is going down by 4. It's a vertical shift. Let's turn to the next equation. G of x is equal to the square root of x plus 3. And notice that plus 3 is underneath that grouping symbol with that x. So that is one of those problems that is dealing with a horizontal transformation when I'm inside with the letter. So this is a horizontal transformation. Those are the ones that are a little bit tricky. It might deceive you that you're going to go plus 3 this way, but actually we're going to go to the left by 3. Now what did the original square root function look like? It was at 0, 0, 1, 1, and 4, 2. That was the original. So you have to know the originals to be able to then move those. So we're going to pick this up and we're going to move it to the left. 1, 2, 3. So my new starting point here is at negative 3, 0. But the pattern still stays the same. That t-chart with the original was 0, 0, 1, 1, 4, 2. So in relation to the new starting point, I'm going to go over 1, up 1, over 4 from that starting point. 1, 2, 3, 4, and up 2 gives me my new point, and that is going to be my transformation. So again, you have to know the basics. You have to know their common points on the basic graphs, and then being able to figure out this shift and graph it from there. All right, now we have an x cubed. Go back to our basic function. Our x cubed is that squiggle graph that we have going through the origin. And we had the points where it was like 0, 0, 1 cubed was 1, and 2 cubed was 8. Now remember, we also had negative 1, and negative 2, negative 8 because it is symmetric with the origin. And so we are going to be able to now do a shift on that function. There it tells you where the parent function is, what it looks like. And then this inside here is going to give me my horizontal shift, what we just did, because it's inside my grouping symbols. Now, take the opposite of what your eyes are looking at. Therefore, I'm going to go to the right by 1. And this is my vertical shift that I have to take the sign as is, so I'm going to go up by 2. So that original, the original graph that we have, and some people like to do this where they have kind of the original where you see what it looks like and then do the transformation on there. So that means that like this turnaround point, I'm going to go to the right by 1 and up 2. So that gives me my new piece there. Let's do a different color. Then I'm going to go over 1, up 1 from there. Over 2, up 8 would be way up here, but I can also go over 1 and down 1. And over 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. And so when I draw that, now we have our x cubed, and that is our shifted function. Over by 1 and up by 2. Okay. All right, very good. Let's move along with reflections. We're going to look at 2 reflections here, one over the x-axis and one over the y-axis. So we're going to try to see what happens to our original x squared graph when I have a negative in front. So here comes my original. There's where my original x squared was. What happens when I do a t-chart with a negative out front? Well, let's just do our 3 common points, 0, 1, and 2. If I throw 0 in there squared, well, the opposite of 0, since it doesn't have one, is itself. If I throw 1 in there, 1 squared is 1, but the opposite of 1 is negative 1. If I throw 2 in there, 2 squared is 4. The opposite of 4 is negative 4. Now again, we have a 2-for-1 deal with our parabola. So let's see what happens when we graph this. Okay, I want to change colors here. So I have this. Then I'm going to go over 1 and down 1, over 2 and down 4. So that gives me half of my parabola. Now here comes my 2-for-1 deal. That point matches with the 1, negative 1, and that one matches with the one x equals 2. So what's happened to the original x squared graph when I have a negative out front? It has now completely flipped itself down under here to the quadrants 3 and 4. And it is flipped down over this x-axis. Therefore, the y coordinates that we had end up becoming opposites of each other, making this a reflection over the x-axis. So that's kind of a reverse. Okay, y coordinates change to their opposites. We have an x-axis reflection. Therefore, y equaling the opposite of our original function reflects the original graph over the x-axis. Now, similarly, we have this square root function, and what happens to it? Well, if I try to plug in some points, we know that the original x squared, or sorry, the original square root function looks something like that. So I'm going to try to plug in the value of 0. If I plug 0 in there, the opposite of 0 is still 0. The square root of that is 0. If I try plugging 1 in there, the opposite of 1 is negative 1. And what number times itself gives me a negative 1? Well, you might say 1, or you might say negative 1. But when I square negative 1, I get a positive 1, not a negative 1. Therefore, this does not give us a number. Okay? So I'm going to go on the opposite side here and say, okay, well, what if x is negative 1? The opposite of negative 1 is positive 1. So what is the square root of 1? It is 1. What happens if I throw in now? If I put 2 or 3, negative 2 or negative 3 in there, we're not going to get a perfect square. So I'm going to throw in negative 4. Opposite of negative 4 is positive 4. Therefore, the square root of that is positive 2. So what we end up having at negative 1, 1 and at negative 4, 2, we end up now having our graph coming over the y-axis as a mirror. Okay, here was the original. Now I'm going in this direction. So therefore, when my x-coordinates have changed, they end up being opposites of each other. Then we have a reflection over our y-axis. And so therefore, we look at kind of the generic function form. If I throw a negative now on the inside versus the outside, then we have a reflection over the y-axis. Okay? So inside y, outside x, that's what we have. So let's look at these these functions and see if we can figure out what the reflection is and how, or the transformation, I should say, how that changes our graph. So here we have with our absolute value, remember it is my V-shaped graph. The negative is on the outside, and according to what we had down here, if the negative was on the outside of my function, we're going to have a reflection over the x-axis. So here is the original, and just by knowing that I have that negative over the outside, or on the outside, I can immediately go forth and do my function and say, okay, I'm going to reflect that over the x-axis. Now instead of it going up, it is going, now it is going down. So I end up having all of those points reflected over the x-axis. So instead of plugging in all those values, all you have is this pattern work, knowing that this is a reflection over the x-axis. Okay? Now, if I have a negative on the inside of this piece, now it's not completely on the outside, it's on the inside with x, we're going to have a reflection over the y-axis here with this one. So what did our original cube root of x look like? That was where we had kind of that little sideways squiggle. And you can go back to those original values, in which it was negative 8, negative 2, negative 1, 0, 0, 1, 1, and 8, 2. That gives me those originals. But now I'm going to reflect this over the y-axis. So that means this 8, 2 over here now becomes a negative 8, 2, because those x-axis, or those x-coordinates are changed to their opposites. This 1, 1 now becomes a negative 1, or negative 1, positive 1, excuse me. 0, 0 doesn't change anything because we don't have to change 0 because it doesn't have an opposite. And then we have this point at negative 1, change the x-coordinate to its opposite, gives me this 1, negative 1. And our negative 8, negative 2 makes it a positive 8, negative 2. So the x-coordinates of these end up changing to their opposites, or you could just go ahead and flip that over the y-axis when you know there is a reflection over the y. Okay? All right, very good. Now, this next one goes back to the absolute value, so we have a V shape. But notice we have this piece, and that piece. So there's three things happening on this function. We're kind of molding things together here. So the negative out front is exactly what we just kind of did on the first problem. We have a reflection over the x with a +2 on the inside. We just did that when it's grouped inside with the x. That's our horizontal transformation. But that is the one that we have to take the opposite of what our eyes are looking at. So instead of having instinct of going +2, we have to go backwards 2. We have to go left by 2. And this is our vertical transformation. So this one we take the sign as is, therefore we are going to go up by 2. Okay? So let's see if we can do that all together. Here was our original V. Okay? I'm going to move that to the left by 2 and up by 2. So this becomes that turnaround point, the bottom piece of my V. Now, instead of that going up, over 1, up 1, over 2, up 2, and getting my matching points, I'm going to go ahead and do the reflection and say, okay, now I'm going to go over 1 and down 1, because it's going to have to look like an upside down V. Over 2 and down 2 gives me that new point, and I get a 2-for-1 deal because it is symmetric. Therefore, that is my function for that transformation. Okay? So, the more you do, the easier it gets. You just have to remember to transform those. All right. Now, let's talk about some transformations when we are kind of changing the size of our function. So, we're going to first look at a vertical stretching and shrinking. And so, notice for our first one here, vertical stretching and shrinking, we're going to use our U-shaped parabola, but notice I have a 2 and a 1/2. So how do those things change? Well, I'm going to do a T-chart here for that, and I'm going to remind myself what the original points are on my parabola. So if I were to put these into my original x squared, I get -2 squared is 4, -1 squared is 1, 0 squared is 1, 1 squared is 1, and 2 squared is 4. Now, what happens if I put each one of these into that function? Okay, if I put -2 in there, squared is 4 times 2 gives me 8. -1 in there, squared is 1 times 2 gives me 2. 0 squared is 0 times 2 is still 0. And when I plug 1 in there, 1 squared is 1 times 2 is 2. And 2 squared is 4 times 2 is 8. So what did I do to these original y values when I had a 2 out front? Basically, we take the original and we're multiplying them all by 2. Okay? So what does that do to my graph? Well, if I go -2, 8, it's kind of up here. -1, 2 is here. Instead of -1, -1, now it's up at 2. 0, 0, 1, 2, and 2, 8. So what happens from the original kind of looks something like this. So notice that we've stretched that parabola a little bit in order to get our new transformation. Now, what happens if I have a 1/2 here? Well, I'm just going to look at the original, like these kind of simplified t-table for my parabola, because I do know I have a 2-for-1 deal. I can get the other points by symmetry. If I plug 0 in there and I square it and then I multiply by 1/2, this new 0 still becomes 0. If I put 1 in there, square it, and multiply it by 1/2, that 1 now becomes a 1/2. And when I put 2 in there and square it, I get 4. 1/2 of 4 is a 2. So what I've done again is taken that 1/2 and multiplied it by all of these to get my new values on my graph. So I get 0, 0, over 1, up a 1/2, which is about there, over 2 and up 2, and then I get my matching points over here to make my U for my new function. So what I have now done of the original, remember, was something like this. So we have now kind of squashed that down or shrunk that function from the original to get the new transformation. So here's kind of the generic pattern. If we have a function f and a c, which is some real number, then if c is bigger than 1, that means we're looking at this 2 over here. What did we do? We stretched that. The graph of y equaling c times f of x, notice the numbers on the outside, is a vertical stretch by multiplying each of the y coordinates by c. Now, also, and that's going to be the same for each one of these, And we're still going to have c on the outside because this now is symbolizing this 1/2 example when I'm between 0 and 1. Then my function y equaling c times f of x is a vertical shrink. It is vertically shrunk. Sorry if I get my grammatical stuff correct. By multiplying each of the y coordinates by c. So basically, we are looking at kind of squashing it or making it a little bit like stretched, a little bit skinnier than the original when we have a shrink and when we have a stretch respectively. Okay? All right, now finally, we're going to be looking at a horizontal stretching or shrinking. And this is not, as always, widely used, but it is a common pattern as well. So we're going to let f be a function c, and we're not going to investigate this. I'm just going to kind of tell you how it works. When you are now looking at the numbers coming on the inside with our function. Now, if c is greater than 1, and we also have when c is between 0 and 1 as a fraction, then the graph y equaling f of cx, so again, notice where the c is, it's on the inside here, is horizontally shrunk by dividing each of the x coordinates by c. So now there's kind of two things. We're dividing now the x coordinates. Instead of multiplying the y coordinates by c, we are dividing the x coordinates. So that's why this one's a little bit different. Now, if we have y equaling f of cx, when our c is between 0 and 1, now we are going to horizontally stretch. So these are actually different. They are opposites from when we were doing the vertical shrinking and stretching. So we're going to stretch that by dividing each of the x coordinates by c. Okay? So we're going to do this kind of by example with the graph that we have here. It goes up and down and then back up. We need to notice that here our c value is equal to 2. And what does that mean? Since that number is bigger than 1 on our function, we are going to shrink that graph by dividing each of our x coordinates by c. So let's just do a t-table of our points, okay? So I'm just going to grab the points from over here. So I'm going to get -2, 0, 0, 3, 2, 0, 4, -3, and 6, 0. Those are the points just from that graph, okay? Now, since we have a vertical shrink with c being equal to 2 or bigger than 1, we're going to have a horizontal shrinking, then we are going to divide each of my x coordinates by c. So we need to divide them in this case by 2. So this divided by 2 is -1. 0 divided by anything is still 0. 2 divided by 2 is 1. 4 divided by 2 gives me 2. And 6 divided by 2 gives me 3. Creating the new points that I need on my function in order to graph this new function. So -1, 0, 0, 3, 1, 0, 2, -3, and 3, 0. So what I've done is basically squashed it like an accordion, okay? You can graph that original, but looking at a comparison between here and here, you can see that this one has been squashed together horizontally, okay? All right, now here, that is of the form f of cx. So c here is equal to 1/2. Because it is between 0 and 1, we're going to have a horizontal stretch by dividing each of our x coordinates by that c. So again, if I look at that t-chart of the points of the original, -2, 0, 0, 3, 2, 0, 4, -3, and 6, 0. So what I need to do is take all these x coordinates and divide by 1/2. Now, when you divide by 1/2, when we divide by two fractions, remember the rule to multiplying fractions is you have to multiply by the reciprocal of the second. So that means I have to multiply by 2. So dividing by 1/2 is the same as multiplying by 2. So that's what we need to do to each one of these points, or these x coordinates, to get my new coordinates of my graph, okay? Now, I've changed the scale of this graph here just so we can account for the 12 and the 8 and such. So if I go -4, 0, 0, 3, 4, 0, 8, negative 3, and 12, 0 is about there, then hopefully it's not the exact same coordinate plane, but you can see that it is stretched out according to those values that you started with. We do have a horizontal stretch when I have this 1/2 in there. Okay? All right, let's do a couple more of those with these kind of graphs, and then we'll do multiple ones of our parent graphs. All right, so notice here we have this function which looks very similar, but here what are we going to have to do with the transformation? Now notice I don't have c being multiplied by x, nor do I have a c on the outside, so I do not have to deal with any of those horizontal or vertical shrinks or shrunks. But I do have to deal with adding something to the inside and to the outside. So as a reminder, this is my horizontal shift or transformation. Take the opposite of what you're looking at. We are going left 1, and then this tells me to go down by 1. That's my vertical shift. We take the sign as is, so we're going to go left 1 and down by 2. So that means I need to I'm just going to navigate through these points. So here's my original negative 4, 0. If I go left 1 and up by 2, I now have this new point. At negative 2, negative 2, the transformation tells me to go left 1. Whoops, I did up 2 instead of down 2. Excuse me. Sorry. Okay, go back. Negative 4, 0. Let's go left 1 and down 2. I apologize. Go to the next point of negative 2, 0. So negative 2, negative, I said negative 2, 0. Negative 2, negative 2. And then go left 1, down 2. Gives me that new point. My next point is the origin. So I'm going to go left 1, down 2. The next point is 2, 2. So I'm going to go over 2, up 2. Go left 1, down 2. Gives me my new point. And this last point at 4, 0. Go left 1 and down 2 gives me this new point. Therefore, here is my graph that I've easily transformed just by knowing those patterns. Okay? Now, notice what we have on this next one. We have a negative 1/2 out front. So remember, that ends up being, with the 1/2 out front, that's one of our vertical shrinks. Vertically shrink. And we also have a negative. So a negative on the outside completely was that reflection over the x-axis. Now, you can do this all at once if you want. If you want to kind of do a T-chart, remember, with the vertical shrink and shrunks, we were multiplying our y values by that c. So if I were looking at each one of these points, this is off the original graph. All I'm doing is looking at these points over here and writing them down in a T-chart. We can take care of that. Remember, f of x is the same as y. We need to multiply that by negative 1/2. So I'm going to go through here on my y values and multiply by negative 1/2. Well, the zeros are nice because they all stay 0. Multiply by negative 1/2 actually gives me a positive 1, and this one gives me a negative 1. So you can actually kind of work through that, multiply using your calculator if you have to, and that gives me my new points. So negative 4, 0, negative 2, positive 1, 0, 0, 2, negative 1, and 4, 0 gives me that vertical shrinking, where I kind of squashed it vertically, and I also reflect it. Notice that it went up, then down, then up, which is the opposite of what the original was, which goes down, then up, then down. Okay, so it all works out with that reflection. All right, let's move on to here. Two things that happen in this function. I have a negative out front, which is a reflection over the x, and I have a +2 on the inside, which is my horizontal. Left or right, take the opposite of what you're looking at. That is a -2. Now this is a parabola because I have that square, so it's going to be that U shape, and that original U shape means I'm going to reflect it over the x-axis, so now it's going to go down, and then I'm going to go left 2. So the original origin, go left 2, and remember what that kind of pattern was for a parabola, 0, 0, 1, 1, 2, 4, but now we need to reflect that. So instead of going over 1 and up 1, we're going over 1 and down 1, over 2 and down 4, and we have our 2 for 1 deal, which gives me those other 2 points. So that is my graph for that function. Okay. Next one, I've got 2 things that go with this. So notice a minus 4 at the end. It is not grouped within the x. So it is not a horizontal shift. This is our vertical shift. And it is going to go, yes, down by 4. And I have a 2 out front with my x squared. It's not on the inside. There's no parentheses there. So that is a vertical stretch by 2. Now, remember with your vertical stretches that we are multiplying our y values by that. So this is another parabola. So here's my pattern. You got to know that original t-chart where you just square each of those values. 0 squared is 0, 1 squared is 1, 2 squared is 4. And so I'm going to now multiply all of these values by 2. So I get a 0, a 2, and an 8. Anytime you have the c out front, multiply by 2. Now, we have to first go down by 4. So the original vertex, that turnaround point was at 0, 0. So go down 1, 2, 3, 4. And from this point is where we're going to use our chart. Okay, over 1 and up 2. Over 2 and up 8. That would be at a positive 4. And I'm now going to do my 2 for 1 deal and get my other 2 points. And now what I've done has vertically stretched that parabola and moved it down with the with the 2 in the front and the minus 4 respectively. Okay. All right, let's try this next one. Now we have a square root function, which is this guy, don't forget, on our basic functions, starting at 0, 0 and going to the positive direction. But what have we done to it? Notice inside here I have a minus 1. That's very similar to this guy where we went to the left by 2. So this, we take the opposite of what we're looking at. Tells me I'm going to horizontally shift right by 1. And this one, take it as is. Means I'm going to go up by 3. So this original, if you want to graph the original, remember, you can do so. I'm going to take that to the right 1 and up by 3. So from 0, 0, over 1, up 1, 2, 3. Now, you can do that for each of your points if you want, but you can also remember that our t-chart for a square root looks something like this. And from this pattern, you can go over 1, up 1, over 4, up 2. It gives me those common points, and that's my graph. Okay, sorry that does that. All right, very good. Let's try this absolute value one. Absolute value has 2 things going on with it, actually 3 things going on with it. Don't forget to see this little guy out front. Now remember that negative out front is a reflection, and it's more specifically a reflection over the x. This negative 2 on the inside, just like we had on this parabola up here, was a left or right shift. Take the opposite of what you're looking at. Means we're going to go to the right by 1. And that 2 gives me a vertical stretch when it's on the outside, okay? So that means that in our original absolute value, we have 0, 0, 1, 1, 2, 2. That our y values get multiplied by that 2. Now, since it has a negative, go right ahead and multiply it with that negative because that will, in a sense, give us our reflection as well, which is kind of nice as well. All right, so here's the original V shape that we have, right? So this is my original. So we are going to go to the right by 2, and this is going to get our reflection, okay? So if I go to the right by 2, there's my new turnaround. This little turnaround point now goes here. So from there, that's my 0, 0. Then we're going to go over 1 and down 2. Over 1, down 2. Over this way and down 2 gives me the matching point. Now I'm also going to go over 2 and down 4. And over 2 and down 4. That gives me my new transformation with that absolute value. All right, moving on to a cube, an x cubed. If you want to remind yourself of what those common points were, we end up having, whoops, make that a 1 and a 2. When we cube everything, negative 8, negative 1, 0, 1, and 8. Now, that's the original piece. The only thing I'm coming in with that is a 4th on the outside. So that means I'm going to take those x cubed values that I just wrote down, and I'm going to multiply them by a fourth. So multiplying by a fourth is the same as dividing by 4. So I get negative 2 on that one. I get negative 1/4. 0. Multiply by a fourth, I get a fourth. Multiply by a fourth, I get a 2. So when I graph these new points, negative 2, negative 2, negative 1, negative 1/4 is about there. 0, 0, 1, 1/4, and 2, 2. What happens is that I vertically shrunk this x cubed graph from the original. So the original would look something like that, okay? So we have vertically shrunk that graph for there. All right, let's do the same thing with a cube. Now notice here we're going to vertically shrink that graph again, now by a half, but we also have 2 transformations. So we're going to vertically shrink by a half. Then this minus 2 means we're going to go to the right by 2. We've seen those numerous times, and this one on the outside is my vertical down by 2. So I'm going to kind of take that original 0, 0, go to the right by 2 and down by 1, right by 2 and down by 1. So now we're going to kind of do something like this. But because I have that 1/2, that means that I have to take half of all my values. So negative 2, negative 8, negative 1, negative 1. These are the originals. 1, 1, and 2, 8. Then I'm going to take half of all these y values. So we're going to go negative 4, negative 1/2. This still stays 0, 1/2, and 4. So from here, now remember, that's from kind of your basis. This 0, 0 is right here. So we are going to now go, instead of over 1 and up 1, we're going to go over 1 and up a half. That kind of gives me that piece there. Over 2 and up 4, 1, 2, 3, 4, instead of going all the way to 8. And we go over 1 down a half. Over 2 this way and down 4 gives me this point here. And we graph it to get our transformation. So again, instead of plotting points on all of these, you are more than welcome to do the patterns. And that's what I want you to kind of practice with. Okay? All right, this last one is my cube root. This going to the right by 1, this going up by 2. So we go to the right by 1 and up by 2. That original cube root of x graph looks something like this, where I was at negative 8, negative 2, negative 1, 0, 1, 1, and 8, 2. So we did something that looked like this. Now we are going to move all of that to the right by 1 and up by 2. So right by 1, up by 2. So I'm going to take the original ones of those, our original cube root ones. I got to reverse all those. So negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. So from that new turnaround point, that's my 0, 0. Over 1, up 1 for the 1, 1. Negative 1, negative 1 from that new point. Over 8. So that would give me to 9, up 2 would give me this point. And over 8 this way, which would be like at a negative 7, and down 2 gives me this one. And that gives me my new squiggle. So it's kind of a little bit different just because it's so stretched out on all of that. Okay? All right, very, very, very good. Now let's turn our attention to kind of going backwards. Given a graph, can you write the equation of that? And then also talk about some even and oddness for functions. So if we look at this graph, we know first off, hopefully by the look, that it has to have an x squared in it. And we've also moved that over some and down some because the original, remember, was this. So where did we go? There's no reflection because it's still going up, but notice, where did that vertex go? It went over 1 and down 3. So we went to the right by 1 and down by 3. So let's see what happens in our function in order for that to occur. Now, let's also double check. Did I go over 1 and up 1 from the vertex and over 1, 2, up 1, 2, 3, 4? Yes, I did. Therefore, there's no number out front. I didn't shrink or stretch it whatsoever. So by a shift of right by 1. Remember, that is on the inside piece. I have to put the square on the outside, and I have to do the opposite of what I was looking at. So instead of doing a plus 1, remember we have to have a minus 1 inside there to be going right by 1. And then to go down by 3, we take the sign as is, and that gives me my function. Now, can you take that and go back and make sure it checks with what your graph looks like? Absolutely. Next one, we have a V shape going on here. So notice, here's my original. What have we done? Well, on the original, I go over 1, up 1, over 2, up 2. That looks good. That means, again, I don't have a number out front, no vertical stretch or shrink. So what have I done from this original? I've gone left by 1 and down by 3. So we went left by 1 and down by 3. So this time on my function, I have to have the absolute value bars to symbolize the absolute value. But when I go left by 1, remember, inside there, it's opposite of what we're seeing. And then minus 3 for my downward shift of 3. Therefore, that would be my function that I have. Now, this next example looks like that square root function. Remember, is that, okay? So we have a square root of x here within there. But did I do any horizontal shifts? Nope, looks like I just went up by 1. But instead of, if I go up by 1, that gives me this, but I also moved it over here and did a reflection over the y-axis. So if you go back to your notes a little bit, remember a reflection over the y-axis, we didn't see that too much, was when we have a negative inside our grouping symbol with the x. So for this function, now, did we go over 1 and up 1, over 4 and up 2? Well, we went over 1 and up 1, over 4 and up 2. Yes, okay. So we don't have to have a number out front, but in order to do that reflection over the y-axis, remember that negative has to come on the inside. And then if I do a vertical shift of up 1, remember that is completely on the outside of your radical. It has to be at the end, plus or minus with that plus 1. Okay? All right, and our last one is a parabola. The first thing I see is it's upside down. So I know I've done a reflection over the x-axis. I've also shifted it. So from the original origin, we went over 3 and up 1. So we went to the right by 3 and up by 1. So we'll have to account for that in our equation. But notice also, if I go over 1 and down 1 and over 2 and down 4, I'm not there. I went over 1 and down 2. So instead of having it at 1, I've multiplied it by 2, so we need a 2 out front, okay? So we've multiplied by 2 here, our y values. So how does that look in our equation? Well, if I multiply by 2, that means I have to have that 2 out front. But notice I've also done a reflection over the x-axis, so I also need a negative there. And then I have a horizontal and vertical shift. So the square has to come on the outside of those parentheses. Going to the right by 3 warrants an x minus 3. And going up by 1, we take the sign as is with the vertical shift, and that gives me a plus 1. So negative 2 quantity of x minus 3 squared plus 1 would be our final answer there. All right? All right, this is a long section. They threw a lot in there. Now we're going to kind of talk about even and oddness, which we've kind of alluded to some of this a little bit, but we're formally going to define it here. So some functions exhibit symmetry in which reflections result in the original graph. For example, reflecting our toolkit functions of x squared and the absolute value of x about the y-axis will result in the original graph. So about the y-axis, that means that here, if I were to flip it over the y-axis, we get the same thing. Therefore, we call this symmetry over the y-axis. Now, likewise, if we look at our graphs x cubed and the cube root of x were reflected over both axes, the graph would be the original for its result. Now, this is what we call a symmetry over the origin. So if we flip over the x, flip over the y, we get back the original. And that is also kind of going to help us with our even and odd functions. So we call a function even if f of x equals f of minus x. So if I throw negative x into my original function, I kick back the original function, we have a graph that is going to be symmetric over the y-axis, very similar to that x squared and that absolute value of x. If we have a function that is odd, then our original function by definition is found by doing the opposite of f of negative x. So this should make sense that we have the reflection over the y and the reflection over the x. That is reflecting both places, which constitutes a symmetry over the origin. Now, you can look at this in a function notation form, or you can also look at it in a graph form, okay? If you kind of look at this one, it's very easily seen that that's the mirror over the y-axis. So we would constitute this as an even function. Looking at this guy right here, notice that an idea of an even function, if I were to flip it over the x and then flip it over the y, then I'm going to get back the original. Now, I always like to do this as this. I look at these points. That's the point 2, 2. If the point 2, negative 2 is on there, then we end up having an origin symmetry. So it's like opposites have to be on there. And in that case, this point would match with that point over here. So this would be symmetry over the origin. Now, there are some times when neither occur. If I were to do y-axis, obviously that's not a mirror for that function. Nor is, if I have the point 3, 1, the point 3, negative 1, negative 3, negative 1 is not on there. So this is just neither. I will tell you there are more functions out there that are neither than the odds and evens. A lot of times you'll see those functions which are neither. Now, if I give you a function, can you tell by using the property of f of negative x what that is equal to if we're going to have even or odd functions? Well, we can do that. The reason we have to do it by a function is we have to plug in that negative x. So I get negative x squared minus 2 times negative x plus 1. So when I evaluate that and say, okay, negative x times negative x is a positive x squared, but a negative 2 times a negative x is a positive 2x, and then plus 1 stays the same always, comparing this to the original, first off, is that equal to f of x? Absolutely not. It is not equal to f of x, okay? So that doesn't work. Then if I have if I try to see if that is the opposite of f of x, then that doesn't work either. So this is a neither function, okay? Nor is it equal to the opposite of negative f of x, okay? Too many parentheses there. Okay. Now, if I look at doing f of negative x, see what that is equal to. That, if I throw into this function, gives me 1 over negative x, and then again, constant stays the same. So I can bring a negative out front of a 1 over x plus 2. Now, if I look at taking out, oops, excuse me, I have a typo here. Let's make that a negative x, excuse me. Sorry. You're probably screaming at me. On my paper I had it wrong. So if I put in an x there and a negative x when I evaluate, this then becomes a minus 2x. So what I can do is actually take a negative out, since both of those are negative, and when I take a negative out, what I'm left with is the opposite of the original. Well, if it's equal to the original, then it's even. If it's the opposite of the original, kind of what we were doing with our opposite points here, this is what constitutes as an odd function. So this 1 over x plus 2x is going to equal an odd function. And then finally, if I look at negative x here, and I throw negative x in each one of these, notice that anytime we take the absolute value of anything, I end up having basically the same thing. It doesn't matter if I have the positive x or the negative x in there, I'm still going to kick back the original piece. Now, negative x squared gives me a positive, so this whole thing is positive times that negative is still a negative x squared and then a plus 5. So if I look at this and I compare to the original, then f of x is equal to the original of x, and that therefore constitutes an even function. So not that we'll go too deep on that with those, but making sure that you're ready, recognize some functions and hear those terms even and oddness. So we are done with section 1.5. We will then move into section 1.6, which is on inverses. Until next time.